Where is it? Where is it? Where is it? I can never find the right emoji at the right time. Do you ever face this issue that you cannot find the right emoji while you are texting? It happens a lot to me. Ask my friends, I take a long time to write a text message because most of my time goes in finding the right emoji. So I thought, why can't we do something about this? And that's when I came across Emoji Prediction model. And that is what we are going to do in this video. In this video, we are going to make a machine learning model which will predict an emoji based on a given sentence. So our model will understand the sentiment behind the sentence and then predict a right emoji for that. Now, isn't that sound cool? It sounds cool to me. And obviously we are not going to create a mobile app for this, but you can definitely do so if you are interested. In this video, we are only going to look at the deep learning model behind this. The main aim of creating this video is to help you understand how you can use pre-trained word embeddings in your model and also how you can use LSTM in your model. And if you're new to this channel, you know the deal. Hit the red subscribe button and also hit the bell icon because I upload new machine learning videos, exciting machine learning videos just like this. And let's not wait further and let's get started with this video. So for this video, we are going to make a very simple application in which we will predict one emoji based on the given sentence. We will only take these 5 categories of emojis for now. This is a very simple dataset that I have taken from the deep learning Coursera course from Andrew Ng. You will find this dataset in my GitHub repo that I have linked down in the description box. Now the reason behind using this very simple dataset is that the main purpose of making this video is to help you understand how you can use pre-trained word embedding in Python and how you can create an LSTM model or a simple recurrent neural network model. And if you are very interested and if you want to make it a little bit more complex, use more data set, then you can use this Twitter emoji prediction data set. I have linked this data set right here in the GitHub repo. So if you open that link, you will find it will take you to this page. You can see that this dataset has 20 different emojis. If you use this dataset, you will have to do some kind of pre-processing data cleaning and you will be good to go. In the future video, I will cover how you can do these data pre-processing and data cleaning. Alright, that was enough. Let's start with coding and we will first import our libraries. So I've imported NumPy, pandas and sequential model, dense layer, LSTM layer, simple RNN layer and embedding layer. I will explain all these layers as we use them. Now I will import our data using read CSV. I have specified header equal to none because if you open our dataset, then you will see that there is no header on top. So you also should do that. Now here you can see that these integers represent the category of the emoji. So let's create a dictionary that will map this category number to the emoji, right? And to do that, we will need to import the emoji library that is available in Python. So I will import emoji. You might not have this library on your system. You will need to install it using pip install emoji. So make sure you install emoji using pip and then only you can use it. Now emoji library has function emojize where you can print any emoji. For example, you can print red heart and it will print us that heart, right? So let's quickly create a map between the integers to our emojis. So for that, I'm going to use a dictionary which I will call emoji dict. And then I'm going to create a function named label to emoji where we just have to specify the label, that's the category number, and return an emoji for us. Thus here we will write emoji dict and pass that label. So emoji dict specifying that label will extract this string and that string will print the emoji. Okay, now let's separate X and Y. X will be the sentences and Y will be the labels. So if you have watched my previous videos, or if you are good at this, then you will know that we have to specify column name and write values that will just give us, that will return a numpy array with that column values. So X will look something like this and Y will look something like this. Then it's time to now it's time to use word embeddings. We are going to download and use pre-trained word embedding called Glove that is made using Glove technique by Stanford researchers. So to download that, you will see the link in that GitHub repo here. So you can see this first link right here. What you have to do is you have to copy this link and paste it in a new tab, and it will automatically start the download. I have already downloaded it. It's around 820 MBs. So make sure you download that. And once you download it, it's gonna look something like this. Now I will explain what are these things. This 50D right here specifies that a word embedding vector is of size 50 dimension. Similarly, this 100D, 200D represents the size of the word embedding vector. In this video, I'm going to use this 100 dimensional vector. So what you have to do is you have to extract this folder and you have to copy this file to the folder where you are working. I already have it copied, so I'm just going to use it. So once you have that file in your working directory, you can just open it by normal open in Python, specify the file name. Now here, to open this file, you have to make sure that you use a UTF-8 encoding, otherwise you are gonna get an error. So make sure you use this UTF-8 encoding. Then I will read the content of the file by file.readlines. Close file, print the content. So here you can see that for every word there is a vector. So here you can see that there's a word the, and there is a vector of size 100 dimension. Then there is the word comma here, and then a word embedding vector for the letter comma. And similarly, there are other words and word embeddings for them. So what we are going to do is we are going to create a dictionary that will map the word with their corresponding vector. I will name this dictionary as as just embeddings. And I will iterate through every line in our file and do line.split. So what line.split does is that it splits a single string sentence into different tokens and store all those tokens into a list, and it separates the token by space. So what I mean from this is that if I print a now splitted line, you will see, so here if you see, a single line is separated by space and all those tokens are stored into a single list. So now what we have to do is we have to just separate this first word with the rest of the vector. So that's very simple. We will just write a line of 0 that will give us that first word, and we will map this first word with the rest of the tokens in that list. But I will also convert this into a numpy array, and I will specify the data type as float because right now it's string. So you can see our dictionary is ready, which maps a corresponding word with their word embedding vector. So we have our word embedding dictionary ready. Now we have to do two things. One thing is that we need to convert the input data X in a form of tokens, because remember I told you that we cannot directly pass this input text because model will not understand that. So we'll have to convert this text into input tokens, and we'll also have to convert this Y into one hot vector. And to convert this input text into tokens, I'm going to use a tokenizer that is available in Keras. So what is a tokenizer? Tokenizer is an inbuilt library in Keras that directly convert this sentence into tokens, which means that it will convert every single word into a specific number. And that number will be assigned according to the order at which the word appears in the dictionary. If you have watched my previous video, then you might have known how we did it manually in Python from scratch. But this time we are going to shortcut the process, and we are going to use an inbuilt library. So tokenizer is a class which is available in keras.preprocessing.text. Sorry, it's text singular. So let's use tokenizer. As it's a class, we have to initialize an object. Now we have to fit this on our data set. So the function to do that is fit on text, and we pass the data which we want to tokenize. Now if I write tokenizer.word index, it returns a dictionary that maps the word to the corresponding index. So here you can see that all words are mapped to a token number. So I will store this dictionary in word to index that tells me that word is converted into index. Now we need to convert that all sentences into a list of tokens. So that can be done by tokenizer.text to sequences, and you pass input x. So you can see that those words are converted into numbers, but I will store that into, I will name it, let's say, x tokens. All right, now if you see x tokens, they are of different length. Now we cannot use this in our model because our input should be a fixed length input. So we are going to pad all these sequences to a fixed length, and that fixed length will be equal to the maximum length of a sentence in this entire data set. So let's calculate the maximum length of a sentence in our data set. For that, I'm going to create a get max length function. We'll pass input x, let's call it data, and then I'm going to iterate over this data and update max len variable as the maximum of max len to length of data. Length of sent. Return max len. So the maximum length of a sentence is 10 in our data set. So we will pad all these sentences up till the length 10. And to pad the sentences, I'm going to use a pad sequence function that is available in Keras. It's available in keras.preprocessing.sequence, and its name is pad sequences. I'm going to call it as xtrain and call pad sequences. Specify max len equal to max len, which is to 10. And here there are two arguments. One is called padding. I want padding to be post, and other is truncating, which in our case is not gonna be there, but still I will specify that. So to let you know that there is a truncating argument available. What truncating does is that it truncates a sentence to a shorter length. So for example, if the length of the sentence is 12 and the max length is 10, then it truncates the sentence from the end till 10. And xtrain looks like this. These sentences are padded. I'm gonna make this code a little bit cleaner. All right, we have converted x into an appropriate input form. Now the embedding layer that we are going to use in Keras expects the input x in the form of these tokens that we have. The embedding layer will automatically map these tokens to appropriate word embedding vector. So this is the input that we are going to pass in our model. Similarly, to pass a proper input y, we will need to convert y into one hot representation. And again, to do that, I'm going to use an inbuilt function from Keras that's called toCategorical. I'm using Tensorflow.keras because if you directly use Keras, that function is not available directly in Keras, so it's available in tensorflow.keras. So it's tensorflow.keras.utils import to categorical. Now just ytrain will be equal to categorical y, and if I print ytrain, you will see that, oops, I have a spelling error. Now y is converted into one hot encoding form. So our inputs are good. It's time to create the model. Model is, as you know, it's a sequential. And the first layer that we are going to use is embedding layer. Here you have to pass the input dim. This input dim stands for input dimension. This must be equal to the size of your vocabulary plus 1. So remember, the value of this parameter input dim should be equal to the size of your vocabulary plus 1. Here word to index is a dictionary with all the words, so I've taken its length. Then the second argument is in output dim. That must be equal to the size of the word embedding vector that you want to use. Now for us, we have imported a 100 dimensional vector, so I'm going to use that, but we should not hard code this, so I'm going to store this in a variable. Then input length, that's the length of the sentence that it can expect. Here for us it's max length, which was 10. Now so far I have not specified this layer that we want to use a pre-trained word embedding. If you do not specify it, what it's gonna do is it's gonna create a word embedding vectors with random values. It means it will initialize the vectors with the random values, and once you train the model, these embedding values are gonna change, and once you train this model, this embeddings values are gonna change. But we do not want that. We do not want this model to randomly initialize the word embeddings, but we want to use our pre-trained glove word embeddings that we have downloaded. So we have to specify this layer that use that as weights. So here it takes a parameter called weights, where we specify those pre-trained word embeddings. Now what kind of input does it expect? It expects a matrix which has word embedding vectors for all the words in our vocabulary. So what do I mean is that I mean that we want a matrix in which the number of rows should be equal to the size of our vocabulary, and the number of columns should be the size of the word embedding vector. So to create that, I'm going to initialize first everything with zeros. Size of our vocabulary can be obtained by length of word to index. Make sure you write +1, and number of columns are equal to embed size. I'll just copy and paste this in the cell. So I will iterate over all the words and their tokens in word to index. This items just get the key and the value of the dictionary. So word is the key and I will be the value. And I will write embed vector equal to embeddings word. Right? So if you remember, embeddings is our this dictionary which maps word to the corresponding word embedding vector. Right, then I will update this embedding matrix with embed vector. Oh, by the way, I'm really sorry. Here, while I was explaining you, I wrote :2 because I didn't want to print a lot of words. Just remove that :2 and then run this. So the embedding matrix looks something like this, where these are the word embedding vectors. Now I will tell you the reason why we have written this +1 is because if you print word to index, you will see that the index starts with 1 and not 0. So at index 1 is the word embedding vector for word I. We need to pass this embedding matrix here in place of weights. So what this embedding layer is going to do is we are going to pass this sentence in the form of tokens to this layer. So it will map the tokens to a corresponding word embedding vector. And then we want to make sure we make trainable equals false, because we do not want to train these word embeddings. If you make this true, then it's going to change the values of the word embedding vector, which we do not want. So this is our first word embedding layer. Now we can specify LSTM layer or a simple RNN layer. So first I will train the model with LSTM layer. The first argument that it expects is units. I will specify units as 16. And what you can also do is you can create multiple LSTM layers which will be linked to each other vertically, just like how you can see in this picture. So I can specify another LSTM layer with units equal to, let's say, I don't want many units because our application is pretty simple, so I will just keep it 4. Now when we are stacking up multiple LSTM or any RNN layer, then we have to specify the value of this parameter called return sequences. You have to specify return sequences true on the previous layer. Now why so? What does this return sequences do? What it does is that in LSTM the input is passed via number of timestamps. So in timestamp 1 we pass single first word, in timestamp 2 we pass the second word, in timestamp 3 we pass the third word, and so forth. So return sequences make sure that it returns the value in every timestamp. If you make it false, then it is only going to return the value at the end of or at the last timestamp. But when you're stacking up multiple layers, you want to make sure that the next layer utilizes all the values that are returned by the previous layer at every timestamp and not just the last timestamp. So let me show you what return sequences does. I'm going to comment this layer and I'm going to just make a prediction from this model. Definitely it's going to be a random prediction with just any input. We'll use np.ones as an input just to show you how this works. I want to get its shape. So you can see that the shape of this is 10, 16. So there were 10 timestamps because 10 is the maximum length, which means that at every timestamp it returned some input value. Now if I make this false and run this, then you can see 1, 16 as the output, because this layer is only returning the output from the last timestamp. I hope this is clear now. So in short, you have to make sure that you write return sequence equals to true if you are stacking up multiple LSTM layers. So if you have let's say 3 LSTM layers of units equal to 10 for now, then here also you have to specify return sequence equal to true. You only do not have to specify return sequences at the final layer, and I mean final LSTM layer. After this, I'm going to use dense layer. The number of units are going to be 5 and activation is equal to softmax. Then model.compile. Then model.compile, optimizer ordem, loss equal to categorical cross entropy. Matrix is accuracy. Oops. And then just model.fit. We pass xtrain and ytrain and specify number of epochs. Let's make it 100 as the size of the data set is pretty small. Oops, it's model. So it's trained and the accuracy is 100%. Definitely it is overfitting because the size of the data set is pretty small. But let's test our predictions and let's see how this model is working. Let me write some sample sentences. Let's say I write I feel good, I feel very bad, let's eat dinner. Okay, and then we will need to convert these sentences into padded tokenized sequence. So we will use tokenizer dot text to sequences and then pad these sentences and pad it with pad sequences. Then our predictions will be model.predict pass x test, and if I print ypred, it's gonna be a softmax vector, so we'll need to, it's truncating. Now the output ypred is going to be a softmax vector, so we will need to get the argmax from this, which is get the index where the maximum value is present. So we'll write np.argmax x1, and if I print ypred, then you can see that it is these are the tokens that our model has predicted. Let's also convert these tokens into emojis. So let's iterate through the sentences. And we will use our label to emoji function that we created. And we will pass this ypred token. Let's see. Okay, so our predictions are pretty good. I feel good. There's a happy emoji. I feel very bad. There's a sad emoji. Let's say dinner. There's a dinner emoji. Now this was a very small data set. You can you can go ahead and try that Twitter data set. You will need to do some pre-processing like removing the unnecessary words, removing punctuations, and so forth. I will cover this kind of pre-processing in the later videos very soon. But before you go away from this video, there are still some things that we need to discuss, and that is instead of using LSTM layer, we can also use the simple RNN layer. So let's try our model with that, and all these arguments remain same for the simple RNN layer as well. So you can train the model using this simple RNN unit as well. So that's it for this video. I hope you learned something from this. I hope you learned how to implement the pre-trained word embedding, which was the motive of this video, and also how to implement LSTM. In future videos, definitely I will cover projects. Let me know down in the comments below what do you think about this video, or do you have any suggestions or the type of video that I should be making. And if you found value from this video, then do hit the thumbs up. It will help me a lot to grow this channel. Also hit the red subscribe button if you have not already. So till then, I will see you in the next video.